Welcome to qnawire.
20 kilogram suitcase being hauled upward at a 32-degree angle by 160 Newton force. And we have to find the work done on the suitcase by, every force in the vicinity. But first, let's find the work done on it by the luggage handler. So that is work is equal to the force that's exerted on the suitcase times the distance over which that's exerted in the direction of the force. So the force is 160 newtons, and then the distance is 3.8 meters, so that's 160 newtons, so 160 newtons times 3.8 meters. That's 608 Newton meters, and a Newton meter is a joule, so we have 608 joules. And let's actually abbreviate this. This is work from the handler, so W sub H. Right. Now we have to find the work done by, let's see, next I think is work done on the suitcase by the gravitational force. Okay, so let's draw on the gravitational force. Gravitational force acts downward. So that's just a vector straight down. What's interesting about this vector is that even though it's acting on the suitcase down toward the Earth, it's actually not in the XY coordinates that we are, kind of implicitly working with, that go parallel and perpendicular to the ramp. So that's X and that's Y. So the best thing to do here is to break this vector down and take some components. So we're going to just kind of break this up into a vector like that vector, and that vector. Right. I guess let's not use dotted lines. Let's just use real lines. Okay. So the force of gravity is that original black vector. The force of gravity in the y direction is this red vector here. So force of gravity in the y direction. And then this is the force of gravity in the x direction. Right. So the work due to gravity, we'll call this work due to gravity. That's also the force times the distance. But now this is the force of gravity in the x direction times the distance it moved in the x direction. So we have to find that force of gravity in the x direction. So we know the force of gravity there is going to be 20 kilograms mass times g, that 9.8, right? Times 9.8 meters per second squared. That's the total force of gravity. Now we have to take into account the fact that it's actually going in this direction too, right? So when you look at this triangle we've got here, as a 30, 60, 90 triangle, where there's your, sorry, not 30, 60, 90 triangle, right triangle, where there's your right angle. If you look at it like that, then you can actually say that this force of gravity in the x direction is actually the force of gravity the force of gravity in the x direction is the force of gravity times the sine of that theta. So that's times sine of theta, so sine 32. And then we have to multiply it by the distance, which is again that 3.8 meters. So we multiply that out, you get the units in joules there, 394.7. Okay, so I've drawn in the normal force there. This is acting normally to the surface. And what's interesting is since the work that's done by the normal force is equal to the force, like the magnitude of the normal force, times the distance in which the box moves in the direction of the normal force. Since the box doesn't move in the direction of the normal force does not do any work on the box. So we can actually kind of just, the normal force doesn't directly do any work on the box. However, the normal force does contribute to the force of friction on the box. And the force of friction is going to be acting oppositely the direction of motion of the box. That's the force of friction. We'll just give that an F. And you can calculate the force of friction because the force of friction, F, is equal to mu, where the mu is assumed to be this mu k over here. I guess I'll include the k. Mu k times the normal force. So my high school physics teacher used to call this the fun equation. I thought that was kind of cute, so I'll keep it. So yeah, that's the fun equation. We can put our numbers in, and we have the mu k is 0.3, so that's 0.3 times this normal force here. Normal force, remember, is equal and opposite to the force of gravity in the y direction. Yeah, we can calculate that by basically we know the force of gravity, just like we did up here. In the work of gravity, we calculate the force of gravity. This time we use a cosine of 32. You can see that just by looking at this diagram and applying the trigonometry. And so, yeah, let's do that now. So I've written down just the raw numbers there. The frictional force comes out to 50 newtons. So now, when we want to find the work done on the box from friction, we just basically say the work is the friction times the distance it moves in that direction. What's interesting, though, is that the friction is acting one way on the box, and the force and the box is moving the other way. So this work is actually going to be negative. So we see that work due to friction is equal to that 50 newtons times 3.8 meters. And that equals negative 189.5 joules. So now, to find the total work, we just sum up the other quantities of work that were put in there. The one thing that's important to remember is I totally forgot to put in a minus sign for this work done by gravity. Gravity's going down, and the person is pulling up. So it's going in the negative x direction, so that's a negative. Now let's sum them up. So total work is 23.8 joules. Now we're going to have to calculate the velocity of this thing at the top. But to do that, we assume now that all of the work that was put into that block to get it up the ramp that's now the kinetic energy. So the kinetic energy is going to be 23.8 joules. And we know an equation for kinetic energy that involves the mass and the velocity. So we write down that equation, we equate it to work, and now we have an equation for the velocity in terms of the mass and some other numbers that we already know. We can just solve for that velocity now. Let's do that. So we assume that the mass is 20 kilograms, remember, and then just solve for V and plug in the mass, and you get 1.54 meters per second. And that's the velocity after the suitcase has been moved up that ramp. If that seems slow to you, that's, I think, a little bit slower than an average walking speed. You also have to remember, a 20 kilogram bag is more like 45 or so pounds, which is quite a hefty suitcase. Also, 32-degree angle is I think quite a bit steeper than most ramps would actually be at an airport. Also, 0.3 for a coefficient of friction is quite high. So basically, this is like a really burly flight attendant pulling this up there and doing quite well.